Welcome everybody to a brand new week of IS50B. Today we're going to be talking about acceleration structures. Now, last week we talked a little bit about rasterization, and when you rasterize a world, it can get very expensive very quickly. For example, if you've got a person, and the person is in the world, and they're looking this way, the person is usually represented by the camera. The camera usually has a field of view, which has what's called a near clipping plane, a far clipping plane, which is usually much further than I draw here. And this creates sort of a truncated, topped off triangle, pyramid kind of thing called a frustum, like that. And that is, if you've ever set like the field of view settings in a video game and things like that, you've got an angle here for the field of view. And then you've got a far clipping plane and near clipping plane. You got the, whatever the dimensions of your monitor are in the rectangle that comes out like that. Everything within this view frustum should, in theory, be able to be drawn. Okay, so if you have a triangle here and a triangle here and a triangle here, those things should get rasterized and drawn to the screen. If you have a triangle behind you, if you have a triangle off to the side, if you have a triangle further away than the far clipping plane, if you have a triangle nearer than the near clipping plane, those get cut away, clipped away. They're not drawn. If there's something right on the edge, then the triangle gets clipped, and only the part of the triangle that is within the view frustum gets drawn. Okay. This can get very expensive. If you've only got 4 triangles like I have here, it's not too bad. This is quite reasonable, quite doable. If you have a million, a billion, a trillion, it will slow down your game to a crawl. And so if you want it to go fast, you need some way of accelerating this. And there's a lot of different approaches for doing this. Let's start at the very basics, okay? So let's say that you've got a bunny, okay? Let me draw a bunny here. My daughter has been like into bunnies recently. So let's see if I can do a bunny that's like reasonable. It's got a little poofy tail there. What do you guys think? Good bunny? I don't know, the eyes are a little sketchy. And the caffeine kicks in. Here you go. There. Is it better now? Teeth. we'll leave the mouth off. Okay. So if you got a bunny, and this bunny is made of all sorts of triangles, right? You could subdivide these things into triangles. You have a whole mesh that's got millions and millions of triangles in it. You want to be able to draw this quickly and accurately. The first thing you can do is wrap this whole thing in a rectangle. This rectangle that wraps the whole thing is called a bounding box. Now, why does this help? Well, it's really easy to tell if a bounding box, if something's within a bounding box or not, or to see if the bounding box is outside of, let's say, the view frustum. Instead of having to do this frustum culling check for all million, let's say we've got 1 million triangles inside of this beautiful bunny here. It's got fangs. There we go. If this bounding box is like here, and it's outside of the view frustum, you know that anything within the bounding box cannot be drawn, cannot be seen, right? And so you can immediately cut away, get rid of, throw away into the dustbin a million triangles without having to go through this process for every triangle. Do you guys understand? Very simple. It's a very simple test to see if something is within a bounding box. Basically you've got, if this is like column 5 and this is column 10, anything between 5 and 10 is here. Anything lower than 5 is outside of it. Anything greater than 10 is inside of it. And then you can do the same, like maybe this is row 100 and row 200. Anything between 100 and 200 on the row, anything between 5 and 10 on the column is in fact within the box. It's very easy. It's a couple if statements. Yeah, it's way, way faster than doing one of these visibility tests for every one of these million triangles. So there's 2 different kinds of bounding boxes. Thank you, Sean. I appreciate you got what I, let's have some blood dripping on it. Let's do some. It's a Monty Python rabbit. There you go. Okay, so so there's two different kinds of bounding boxes. There's what are called AABBs, and there are OBBs. So an AABB is an axis-aligned bounding box, which means the vertical line here is lined up with Y. You know, if this is a 2D world, you know, the Y-axis is this way, the X-axis is, you know, this way. And so the bottom row of it is exactly parallel with the X-axis. The leftmost column, the rightmost column are perfectly, you know, parallel to the Y-axis. And so this actually makes the math very easy. It makes the math pretty simple. It's just an if statement. You know, if you know, you basically say if you know, x is 5, 10, and if you know, 100 to 200 on the y. So it's just a couple of if statements, and then you know if you're within the bounding box or not. An OBB, yeah, you know me, is called an oriented bounding box. No, I don't think they got. I don't think most of them got the reference. Okay, an oriented bounding box is one in which the box can be rotated like this. And so the bunny. Let me draw the bunny here again. You're exactly correct, Megan. Yes. And so if you have an OBB, then as the bunny rotates, the box can rotate with it, and that allows you to create a tighter fit on the bunny. Because if you have a long, narrow object, like, you know, the bunny here, if you did an axis-aligned bounding box, then you'd have to have the bounding box be quite big to wrap the whole thing. Whereas with an OBB, you can get a tighter fit. Usually I just work with axis-aligned bounding boxes because I like my code being simple. OBBs, you have to like rotate things. So yeah, I mean, you can make it work either way. So this guy here is an OBB, and this one here is an AABB. You guys understand? And so what's neat about these things is came out in 1991. So what's neat about these things is that if you do a bounding box test, you can very quickly throw away all million triangles in Dracula Bunny here without having to go through each one. Okay. And so this is a recurring theme when we're talking about acceleration structures, is we want ways to very quickly discard large amounts of geometry so that we don't have to process them. Do you guys understand what the point of the lecture is for today? Let's make this guy in galaxy blue instead. Old but still lit. Yes. Okay. There's also something called the bounding sphere. And in fact, the first game engine that I wrote used only bounding spheres. And so if you had a bunny like that, then let's do the bunny in a different color. Let's do rainbow color bunny this time. So if you have a bunny, like this, instead of wrapping it in a box, we always wrapped it in a sphere. So you'd have a center point, and you'd have, I'm doing this in 2D, so I'm going to draw a horrible circle instead. More time. A little bit better. Yep. And so it's not quite tight enough that there should not be any gaps, you know, over here, but whatever. And so basically, whenever you have a bounding sphere, then you have a center point, which is usually the center of mass for the object or something like that. And you've got a radius. And it's very simple to tell if a point is within the bounding sphere or not. Again, if you want to know, hey, is this point here inside of the sphere? You take the Pythagorean distance between the point 0.1 and 0.2. And if that distance is smaller than the radius, congratulations, you are within the sphere. If the distance between 2 points, if you guys remember algebra, it's just the Pythagorean theorem, square root of, a squared plus b squared. If that distance is greater than the radius, then it's outside. Pretty simple. So, for example, if you had a sphere over here, you could easily tell if this if the whole sphere is like outside of the view frustum, and if so, you just throw away everything inside of the sphere. Now, one of the things that I did was I added a recursive hierarchy to it. So we had a bounding sphere volume hierarchy. And so if you wanted to like shoot the bunny, you would you maybe fire a gun like this. Here's the gun over here. And you could find these like points of intersection pretty easily. Doing a line intersection is actually a pretty simple algebraic thing to do. And if all you had was a single sphere indicating the bunny, this would be a hit. Okay. And then for a bounding box, again, if all you had is a bounding box, it's very simple to test to see if a line intersects with the box. And so this bunny, would be hit as well, assuming this bunny's on the way. But what I found was that resulted in a lot of space, resulting in hits where they weren't actually part of the mecha. So for example, if you shot up here, all of those would indicate a hit because there was no further level of detail down below the bounding sphere, because bounding spheres were very fast. And so you can make hitboxes. Yeah, exactly. And so these are the hitboxes. Because I never went down to the mesh level to do a intersection test. It was just too slow. And so when people are firing thousands of bullets a second, you don't have time to work with that. And so all I had was bounding spheres. But I made a volume hierarchy, so you could put a sphere inside of a sphere. And so I could put a subsphere here for like the head, and then a sphere here for like the body, and a sphere here for like the butt region. And so if you hit, instead of just immediately returning hit, what it would do is it would then check, does this line intersect this one? No. Does it intersect this one? No. Does it intersect this one? No. Miss. But if it did, let's say hit this one, then I could have further subdivided circles for the 3 subregions in there, and you can nest them as deeply as you wanted to get as accurate as you wanted. I typically only went about 2 levels down because at a certain point when you're shooting rockets and things like that, you really can't see, when there's a big explosion, like did it like miss? Did the rocket fly in between the poofy tail and the leg? Like it just hits and you're fine with it, So, so a bounding box is good. A bounding box volume hierarchy is better. And so this is the standard acceleration structure these days. It's called BVH. Stands for bounding volume, being all fancy here with the vertical hierarchy. Is it I before E except after C? Let's go with that. Hierarchy. BVH. How many of you guys have heard of, you can assign different damage for each sphere? You can. Yeah. So you can have a headshot, and in fact, in Unreal Engine, it'll return which bone you hit and things like that. But even in Unreal Engine, you can choose, do you want to do complex collision or do you want to do simple collision? Simple collision, you hit their capsule that surrounds the person, which is a cylinder, essentially, with a round head and round feet. The feet part doesn't really make sense. Or you can do mesh accurate collision if you want. It just depends if you want fast or if you want accurate. And so even in Unreal Engine, it can return which part of the target you hit, and then you can do double damage if you hit the head or something like that. Okay. So do you store them as a tree? Yes, you do. Yes, you do. So a BVH is similar to what I did. This was, my Fisher-Price baby's first game engine. This was the approach that I took, and it worked okay. Most objects in the game world were not spherical shaped. I probably should have gone with bounding boxes because I had a lot of like rectangular office buildings, which would have been great for a bounding box. But as it was, you know, I subdivided and had 4 like sub spheres inside of it. So if you shot it like right in the middle, the rocket would like kind of go inside and penetrate the building a little bit before it detonated. And then if you shot kind of like halfway down, a little bit outside, it would hit a little bit outside of the building, because I'm trying to like approximate an office building. Trying to approximate an office building. It looks like this with like 4 spheres, kind of like that. And so there were like areas where like it bulged out a little bit, and areas where like the rocket could go inside of it a little bit. It was okay. Is there performance bonuses to using the spheres? Yeah. Spheres are great because you can rotate them and they don't change, you know, so their orientation doesn't matter at all as they rotate around. If you have your bunny rotating inside of the sphere, if all you have is that one sphere, like I said, that bunny can rotate and you don't have to change anything. It makes life really simple. It's a very simple test to detect collision. If you want to see if 2 spheres touch each other, like that, basically you just take the distance between the 2 center points and add the radiuses together and see if it's less, right? And so the radius here, let's say is 3. The radius here, let's say is 8. And if these 2 guys are 7 away, 3 plus 8 is 11. 7 is smaller than 11. Therefore, they're touching. It is really, really simple. Add the 2 radiuses, subtract, you know, and there you go. So you can, yeah, it's a lot of Pythagorean theorem stuff, but you don't even have to do the square root. Square roots are the most expensive part. So this is a little bit of optimization for you guys. You might like it, you might not, I don't know. So like the hardest part of the Pythagorean theorem, let's see it almost, okay. So the hardest part of this is actually the square root in terms of like computation. A multiply is 4 cycles about, the addition is about 1 cycle, the multiply is 4 cycles, and so that's a total of like 9 cycles. A square root could be like 80 cycles. It depends on the architecture. It could be much cheaper than that. I've seen some where it's like a dozen, but it's still like significantly more than the cost of this. And so it's very common for people to actually just never do the square root. And so if you want to tell the distance between, if you have a point 1020 and a point that's at 1030, in other words, you have a point here and a point here, and this guy's like 10 to the right, you know. If you did the full Pythagorean theorem, you would take 10 minus 10, so it's like x1 minus x2 squared plus y1 minus y2 squared, 20 minus 30, 10, and then you square root the whole thing. But a lot of times you just don't square root the whole thing. And so what you end up with is 0 squared plus 10 squared, and you end up with 100. And you compare that against the radiuses squared. And so if the radius of this guy plus this guy's 3, that guy's 8. And so that's a combined of 121. 100 is smaller than 121, therefore it's within the radius. So we never do a square root, right? We just add together this guy's radius, which I don't know if you can see it, is 3. This guy's radius is 8. You just add the radiuses together, square them. You don't have to square root them now, you know. And so that's just 2 cycles here. So that's a 2 cycle cost there, plus 1 for the addition. 1 for the addition, 2 cycles there. 1, 2 cycles for the subtraction. So it's a total of 4, 8, 9, 10, 11, 12, 13, 14. So it's like 14 cycles total to see if 2 spheres intersect with each other. Not bad. Modern CPUs run at, you know, like 4,000 cycles per second. So spinning 14 cycles to see if 2 objects collide is pretty good. Okay. So it's not bad. Not bad at all. And like I said, and then these 2 objects can rotate, and you don't have to rotate the boxes around them. If you rotate with an AABB, if the bunny rotates inside of an AABB, the AABB has to get bigger, and you have to recompute the AABB to fit it. Or you just make the AABB not a rectangle, you make it a square. Or in 3D, you make it a cubic, you know, solid. And then it's more wasted space, you know, and you get false collisions and things like that. So spheres are just really nice for a lot of reasons, but like I said, they don't approximate shapes very well. You know, and some shape, like if you have a round shape, it works great. But for like my office buildings and my mechas and things like that, they weren't very circular, at least not to begin with. After a while, I tended to model my mechas as more, you know, like their arms are sticking out a little bit wider, you know, and so they're kind of filling the sphere that they're in. So, you know, you do what you got to do, you know what I mean? So if that's your technology, you make your art match the technology, and instead of your technology matching your art, right? Unreal Engine, you don't have to worry about these things. It does all that for you. They've already figured all this out. But let's come back to bounding volume hierarchy. So if we were to, is there a reason to mix bounding types? Yeah, I mean, if you got round objects and you got rectangular objects, knock yourself out. It's not actually hard to see if a sphere intersects with a rectangle. So you have a sphere, you have a rectangle, you have a minimum, this is minimum x, max x, x. Basically, you can draw a ray towards the nearest point on the rectangle. There's an algebraic equation to do that. Find me the nearest point on the rectangle to this point here. And then you just see, is the distance of that within the radius? You know, if this guy is 7 away and the radius is 8, congratulations, you are touching the rectangle. So, yeah. And there's books you can buy that have all these different equations. How do you do line, you know, how do you do line rectangle intersection? How do you do line sphere intersection? How do you do line line intersection? How do you do rectangle rectangle intersection? All of these things are the fundamental building blocks of 3D game engines. And all the math has already been worked out a long time ago. And there's websites you can find that have all those different equations on them and stuff like that. Or, you know, if you want to have fun, work them out yourself. Figuring out rectangle intersection is something I typically have students do in CSci 40, for example. Like, how do you determine if two rectangles are touching? That's a good CSci 40 assignment. And it kind of burns your brain a little bit to think about it, but it's not bad. It's not bad. Okay, so let's come back to this, BVH. So instead of having just one bounding volume surrounding the bunny, what you can do is have nested rectangles in it. Because right now, if we were to shoot a bullet like this way, and we were only representing our bunny with the bounding box, that would register a hit. And Bruce, have you seen before, like bounding box issues in video games, where like you shoot somebody like right here, you know, and it's the area between the head and the shoulder, and it registers a hit? Dark Souls 2, yeah. It's frustrating, right? It's really frustrating when you get hit when it's open space, get hit after dodging, or it's also kind of lame when like you shoot between the legs of a giant and it hits them, you know, and you're like, it's just open space, you're shooting there and you're hitting them because the bounding box encompasses it. Shoot his stomach and do no damage. Yeah. So bounding box issues are a big deal. Now, how many people have heard of RTX? So like there's the 3090 RTX, the 4090 RTX. Have you guys ever wondered what RTX on is all about? I'm sure you've seen the memes for it. You know, there's like SpongeBob RTX on. RTX off, RTX on, right? So, front-facing Simpsons. I have not seen that. Should I be showing this on a stream? That's hilarious. All right. Okay. So, what is a BVH? A BVH, you nest multiple bounding boxes inside of each other. Just like what I did with the spheres, you can have a sub box there and a sub box here, like that. And then if you shoot, you have the outer box and it registers a hit. But you're not done yet if you register a hit. If you register a miss, you're done. Like if the shot comes this way, like that misses the bunny, right? You're done. Once you indicate a miss, it's over. And that allows you to very quickly check to see if a bullet hit a million triangles in the bunny, right? You fire the bullet this way and yeah, it misses. Okay, done. But if we fire the bullet this way and we hit the outer box, well, we're not done yet. We have to see if we hit the head and do double damage on Vampire Bunny here, or if we hit the body and do regular damage. And if this was all we had, then if we hit like this area here, it registers a hit. So like this area would register as a hit. But if we wanted, we could go another layer deep, right? So we could go down another layer and have like rectangles for each one of the legs, and a rectangle here, and a rectangle here, and a rectangle here. Like we could go as detailed down as we want, having increasingly smaller and smaller and more accurate rectangular solids, essentially indicating the bunny. Depends how much accuracy you want. Now, what RTX on does is it actually takes a BVH. So BVH is sort of the official acceleration structure for, you know, video games these days, because what you do is you take a BVH for your bunny and you hand it to the graphics card, and that's what it uses for visibility testing and rendering and things like that. So all this stuff you've heard about ray tracing, these lines that I'm drawing here, they don't just have to be bullets. These can be rays from the camera used in rendering. So what happens when you have ray tracing is you can imagine your screen here, and your screen, I'm going to just have a very low resolution monitor here. Let's say that you've got, what is it, 6 pixels wide and 4 pixels high. You know, this is your 4P monitor. Not 4K, 4P. It's like 1080p, but it's 4P. And so 4i. Yeah, it's interlaced. Sure, why not? 1, 2, 3, 4. Yeah, and 6 wide. It's a 6x4 high resolution monitor. Okay. And you can imagine out in the world, you have got rectangles, you got spheres, you got cubes. I'm kind of drawing these things off at an angle. You got different triangles and things like that. And so the way that ray tracing works is you can imagine shooting a bullet from each one of these points on the screen. I'm kind of in like a fake 3D perspective here. You can like shoot a bullet out this way and see what you hit. Oh, look, I hit this triangle here. And from the center of this one, you can shoot a bullet out. Oh, I hit a sphere. From the center of this one, you can shoot a bullet out. Oh, I hit that triangle. Shoot a bullet out. Oh, I hit nothing. Right? And so let's say that this triangle here is red, and that this sphere here is green. I'm just not even worried about lighting right now. I'm just kind of flat coloring them in blue. What's going to happen is this pixel will draw in as blue. This pixel will draw in as green. This pixel will draw in as red. You guys understand? You basically shoot a gun array from the center point of every pixel, and just kind of see what you hit. And instead of kitchen gun, it's lighting gun. Yeah, exactly. You just shoot an imaginary bullet through the world. And, you know, if you like hit a mirror, then the bullet, the photon, can bounce off and hit something else. And like it gets complicated, and we'll have a lecture on ray tracing. But that's kind of the basics of it. Like if you don't have any bounces at all, that's basically it. If it hits nothing, we draw black. If it hits something, we draw whatever color it is. And we'll leave off how we figure out the lighting and materials and things like that to another time. But basically, you just shoot a bullet from every point on the screen and draw whatever's there. Now, how does a BVH help? Well, without a BVH, think about this. If I was going to shoot a ray over here, without an acceleration structure, I would have to say like, hey, does this ray hit me? No. Does this ray hit you? No. Does this ray hit you? No. Does it hit you? No. Does it hit you? No. And so for every ray, it is an order n problem. In other words, if you have n objects in your world, n triangles in the world, let's say we have 1 billion triangles in the world, every ray you shoot is 1 billion checks to see if it hits. And that is ridiculously slow. Okay. So if we have an acceleration structure, though, well, check this out. So let's say we wrap this whole thing here in a bounding box. When we fire this ray over here, we say, hey, did I hit the bounding box? No. Okay, we're done. Black. Right? And for this guy here, I shoot a ray. Did I hit the outer bounding box? Best case, order 1. Yeah. And then we might have like 2 sub boxes inside of here, right? And so I hit the outer box. It's like, okay, I got a hit. Am I done? Well, let's see. Oh, I hit the inner box. Okay. And then inside of the inner box, there might just be 2 objects. And I might just check both of them, right? Like when you get down to it, you actually don't need to have boxes like approximating every single square inch of the surface. You can actually get down to a point where you've just got like 2 objects left in the box. And you just like, hey, does the ray hit this one or this one? No? Miss. Yes? Okay. Which one? Green? Cool. Green. And so here we've just got a couple boxes, and you can see that it's going to take us down to probably like log base 2 of n if we divide every box into 2 boxes. Something like that, right? Every time you shoot a ray, you're essentially throwing away half the objects in the world, right? When my ray comes into here and not into here, well, then I've just thrown away all those objects. Now the ray might miss and come up here. And so, worst case scenario, you might actually end up having to, if all of your objects are on the same location, yeah, it's still going to be order n, right? You guys see that? Like if all of these triangles are like on top of each other, it's probably not going to help, right? But so BVHs work when things are kind of like spaced out, and they're not all glued on top of each other. You guys understand? So it's not big O. It's it's like approximately. It's like on average, log n. But that'll kind of approximate kind of an answer for the running time. So it turns your running time from like order n to something along the lines of log base 2 of n. So if you have 1 million objects in the world, whereas before, what is the resolution of our screen here? We have 24 pixels. So the old way, 24 pixels times 1 million triangles means 24 million tests to see what we hit. This way, 24 pixels times 16, which is the log base 2 of n. Actually, sure. Something like that. Then it's going to be 240 plus 120. 360 plus 24 is 384 tests. Something along these lines. Okay? It's kind of approximately. So instead of 24 million tests, we're doing 384 tests. Do you guys see what a difference in performance this makes? And this is all very back of the napkin stuff, but just to kind of give you an idea. What do you guys think? How much faster is that? It's like 10,000 times faster. It's a lot faster. So, let me pull up that thing here. So 24 divided by 384, 60,000 times faster. So these acceleration structures that we're talking about make a big difference. Now, what makes it even faster is that you don't actually have to do these tests in the CPU. Because RTX hardware cards understand the BVH file format, you can actually push them over to the graphics card. And the graphics cards are beasts. Like graphics cards are way, way faster than a CPU at doing this kind of stuff. And so you can just ship the BVH over to the graphics card and be like, draw this. And it will be able to render the world with ray tracing in a reasonable amount of time. Whereas if you had to do everything in CPU, it's probably not going to be fast enough. So yeah, so what does RTX on mean? It means it can take a BVH file format and do ray tracing on the world. Now, they don't always actually use the ray tracing to do the rendering. They actually, a lot of times, will still use the standard raster-based systems, which means, you take a triangle like this and you put it over the pixels and you fill the pixels, over the screen. Okay, if it has a majority coverage, this guy turns red, this guy turns red, this is minority, so these don't turn red. So a lot of times they'll actually just still use the old triangle-based rasterization techniques because we know them, we understand them, they work well, but they might use the BVH for lighting or for reflections or for, I've seen them use it for like wave patterns out in the world. So the graphics cards can mine the BVH data and say, hey, if I have a mirror here, what should I see, if I shoot rays at it? And so you can layer on lighting on top, from BVH, from RTX on. You can layer lighting on top of your rendering and get very nice global illumination. Like right now, the door behind me is open. And so the lighting in this room comes from, I have a direct illumination from the light above me. You can see if I put my hand up, I'm getting light from the light bulb above me. But there's also global illumination coming in from the doorway back there. There's a window open, light is flooding in from outdoors, the light's bouncing around in the corridor, and then it comes flooding into my office here. So if I were to turn off my office, you would still see some lighting in here. It wouldn't be pitch black, even though there would be no direct lights left inside of this room. So you can use these techniques in combination with each other, and it's really cool. There's a lot, like we're in a brand new world. Like ray tracing was a pipe dream for a long, long time. People would render these like glass spheres, and they would run their simulation for like a weekend, to like come up with things like this. Like these are like classic, ray tracing demos. And so they shoot a ray out and it bounces off the surface and it bounces off the surface. And if you have multiple ones together, let's see, like this, you can see they're like the rays are bouncing off of each other, and it gets very complicated very quickly. Here you have light refracting through a glass sphere and a glass cube, and so these renderings would oftentimes take like a week to do one of these things, And it was always kind of a pipe dream to do like this kind of stuff in real time. And now we've got it. NVIDIA came up with some pretty significant advancements. It doesn't send out as many rays as maybe you think it would. Ray tracing predates rasterization. Yeah, it does. Like ray tracing's been around since forever, but rasterization has been better for real time for a long time now. But now ray tracing is like, it's like a thing, and you get these really beautiful lighting results and things like that when you can have light bounce around instead of having everything just direct lit. So I guess we have a little bit of time. So yeah, let's talk about ray tracing a little bit. So you don't usually just send one ray per pixel. You actually will typically have like multiple rays per pixel going out, and you like average them together, right? And so you might send 7 per pixel or 13 per pixel. Depends what quality you want. So when you do an RTX game, you can turn the quality up to ultra. And ultra quality might send more, well, it will send more photons out per pixel than low quality. Okay. And why does that matter? Well, let's take a look at this. Let's say that you're sending a ray through the world here. And you've got, not you, Sean. And I'm a Raymond to you, and so Sean. And Megan, your husband? All right. And so we shoot this here, and then it reflects up this way. So there's a problem, which is that pixels are actually kind of big, right? And so if you can actually send multiple rays all kind of in parallel with each other, then these are all going to kind of reflect off at different angles off the sphere, right? And so if you've got like, I don't know, like a shape up here, it'll actually make a better representation of the reflection than if you just shoot one, right? And so steals my identity in CSI 40. So it's very common to actually shoot multiple rays from different parts of the pixel, because whenever you get to a curved surface or something like that, it can actually make a really big difference in the reflections. And so let's say that you get to, let's say we're not even going to do reflections yet. Let's just back off on that and just shoot a single ray at just like a wall or something like that. Just a very simple wall. Okay. And this wall is just blue, galaxy colored, whatever. Okay. When it hits this wall here, if we have no lighting, we just draw blue. But in the real world and in RTX games, you have the sun, right? Or you have other lighting effects. So when you hit this wall, the first thing you typically do is you'll send what's called a shadow ray. And so you'll actually send a ray towards the sun and see if you can see the sun. If you can see the sun, then that surface is lit. And you can draw the blue or whatever it is there using the lighting calculation. The lighting calculation, you guys remember what a normal vector is? This way. The lighting is based on the theta here. It is lit. Exactly, Caesar. So the cosine of theta times the sun, basically. Let's just do some pseudo math here. Right, so if the sun is directly overhead, you get full lit. For example, the light above me, like you see how brightly lit my hand is right now? As I turn it to 90 degrees, it stops picking up any of the light because the cosine of 90 degrees is 0, right? Cosine of 0 is 1. And so as my hand goes from 0 degrees, the normal of my hand is this, right? It's perpendicular to the surface of my hand. As the normal goes from 0 degrees towards the light to 90 degrees, you can see it becomes fully shadowed. And the only light on my hand right now is the global illumination in the room, plus the light coming off the monitors. Okay. So you take the cosine of the normal and the normalized shadow ray and multiply that times the light of the sun, and that's how much light you have on the surface, and we'll just call this L. And then you multiply L times the material, whatever color is on the material, and then that is the color you return back to the pixel being drawn here. You guys understand? So if you have a blue surface RGB, red, green, blue. If you have a blue surface, that's the material. Let's say it's just pure blue, bright blue, ugly blue. And then you've got the sun, which is kind of yellowish, which is going to be 0.8, maybe 0.4. That's the light coming off it. Well, yeah, let's say this has already been decreased from the angle. To multiply these two things together, you just take 0 times 8, you get 0. 0 times 0.8, you get 0. 1 times 0.4, 0.4. So the final color you see that gets drawn is like a dark blue. And so that's how you light a surface. Now this gets more tricky when you got other lights in the room. So if you've got a point light over here, a little light bulb over here, it's radiating light. Well, you got to shoot a shadow ray to that one too. So you have to shoot a shadow ray to that and see if that's not a straight line, and see if that is blocked or not. Let's say it's blocked this time. Let's say that there is a block in the way. So when you shoot a shadow ray towards that light, it doesn't make it. And this test, and this test, and this test, all these tests are done using the BVH. And the reason why that's fast is because intersecting a line with a hierarchical bounding volume is very, very fast. Like I said, it's something along the lines of order log n. And so you can see what does this line hit very, very quickly when you got a BVH. You guys understand? So Daniel, post those shots in the help center so they don't come in the lecture. You guys understand? So all of these rays that I'm drawing here, all of these are accelerated by the BVH. And so this guy is not going to get any lighting from this light bulb here. It might pick up lighting from this. If this guy's emanating light, it might absorb light from that. And that leads us to a question of global illumination, which is a question for another time. How does light diffuse through a world? We don't need to worry about that right now. So basically, when you do ray tracing, you're just going to shoot a bunch of bullets through the world, see what you hit. When they hit a surface, they cast a shadow ray to the sun, see if they're getting lighting from the sun. If they are reflective, surfaces, then the light might bounce off and go somewhere else. If they're refractive surfaces, they might refract through a surface. And so instead of just sending one photon, you might end up cascading and reflecting off 10 mirrors and things like that. So there's usually an upper bound as to how many additional ray traces you do from the original ray trace. And that's also part of the quality setting when you're playing a video game. It's how many bounces do you allow? And I think in Unreal Engine, right now, my engine's set to 2 bounces, which is not a lot. But if you have a mirror, it'll hit the mirror and bounce off. And if there's another mirror, it'll bounce off. And then that's it. So if you're in a hall of mirrors, it won't show infinite copies of you. It'll show like 2 or something like that. So, you guys understand? That is kind of the basics of ray tracing. And the hierarchical BVH here is an acceleration structure that makes all of that go fast. So all of these bullets you see, all the rays you see, all of them can find what do I hit in very quick succession, right? And the graphics cards are capable of doing that extremely fast. And so you can shoot thousands and thousands of photons very quickly through the world, gathering lighting information, gathering the material information, and then drawing it on the screen in real time. It's pretty cool stuff. Yep. Send in help, not lecture. Okay. So what your next homework assignment is going to be is you are going to be given... Oh, you don't have an account on the server yet. Okay. So let me just show this. Then I'll CD BVH. Oh, it's called RTX on. RTX on. So let me show you what this looks like. Okay, so let's open up map 1. And actually, let me show you what map 1 looks like. So this is a set of boxes. Okay. And so this box goes from 0, 0 to 100 to 100. And it's got 4 sub-children, boxes 1, 2, 3, and 4. And the row is the box number. So this is box 0, this is box 1, this is box 2. This 0 means it's not a leaf node. In other words, you have to go within it to see if you actually hit something. This box here goes from 1, 1 to 2, 2. This one goes from 10, 10 to 11, 11. This one goes from 130 to 3160. And this one goes from 90, 10 to 110. So you can probably sketch this out on graph paper and see the sub boxes within the big box. So we're going to open up map 1. The file name with the shots. Where is that? Shots. And so this one has a set of shots. That's the origin. 0, 0. It's shooting from the origin, shooting straight up. Shooting straight up. And so it's Y and X, I think. And so it's basically origin and slope. Slope's not the best way of doing things. There's a better way of representing lines and rays than using slope formula, but my students are more familiar with those than with the parameterized expressions. So we'll just go with that. So map 1, shots. And let's fire all the shots and see who's getting hit. So box 2 is hit 1 time. Okay. So that is what you guys have to work on for the next week. Okay. It's basically implementing a BVH volume structure, a hierarchical volume structure, and basically a shot will come in, and if it hits the outer box, then you have to check the inner boxes to see if they hit. One of those hit, you return true. If the outer box misses, you return false, and that's basically what you got to do. You got a week to do it. Okay, so that is this is going to teach you guys really intimately how a BVH works. In the future, are you going to write your own BVH? I don't know, maybe. It's not actually too bad. It's not an easy assignment. I'm not going to tell you guys this is easy, but figuring out line, rectangle intersection, you guys should be able to figure that out. If not, ask me for help and I can help you with the algebra on it. But this will give you an understanding, an intuitive understanding of how RTX graphics cards accelerate things. And you know, if you've ever done 3D modeling, you might have seen a BVH bunny before, like that. So that is what an actual vampire bunny would look like when converted to BVH format. So you got the outer box, and you got the sub boxes, and the sub boxes, and the sub boxes. And then the leaf nodes, the parts that are actually solid, are red. And the white ones are just bounding boxes that aren't, that if you hit them, you still have to check its subchildren to see if you hit something. You keep doing that until either you hit a red box or you miss. Okay? You guys cool with that? Bad bunny. And this is what it looks like when you actually render it. Pretty cool. Pretty cool stuff. All right. 50B people, you're done. 58 people, you're up next.